Okay, so you have this Altium software installed, and I hope everyone has a 4 GB plus RAM for this software. And the one which I'm using over here, you can find out the version over here, that is 20.2.5 over here. If you can get anything else from other torrent, do share that with me also. As far as the Altium is concerned, if I give you a little brief history of this software, back when I was a student at that time, the software name was Total 99 SE. This actually came in the year 1999, and SE was some abbreviation for some company. And if you just Google it out on Google, write it down Total, you will find a lot of old designs of that Total software. I even worked on that software when I was a student, or just after my as a teacher. This Altium Designer, from the last 17-18 years, it has come a long way, and I've worked on Altium 10, Altium 16, and this time it's Altium 20. It's a worldwide renowned software, and almost all companies as big as Apple or anyone, they already are using this software for designing. And if you are very good at this software, then certainly you can even start a freelancing job at even any freelancing website or Fiverr or anywhere you have the skills. And I know many students from session 2017, 18, 19, they know the skill, they know the art, so they have been designing the PCBs. And one thing very important, I guess I told you in the very first introduction also, that this PCB which is in my hand at present, this is a single layer PCB. As you can see, this is a single layer PCB, and the single layer PCB has the tracks at the back. Now the other one I have is a double layer PCB. You can see the tracks at the back and also on the front. Actually this is the front actually, and this is the back, because on the front why it's called, because here you are actually putting that yellow dot matrix or that RGB dot matrix and the SMT components on. This is a 2-layer board. Now in Pakistan or in this lab, whatever you are going to work on it, either you are going to make a single layer board or either you are going to make a double layer board in Pakistan, but practically possible 30-layer boards are also possible. And 30 layer means that between any 2 layers, those 30 layers are going to be inside the thickness of this laminations over there. So then practically 30 layer board in Pakistan, it's not possible. I know one lab at Kahuta Research Laboratories, Keepout Laboratories in Kahuta, they can manufacture a 14 layer board in Pakistan, but again this is only for defense purposes, and they are not agreeing for any educational or any scientific works over here. But if you want to make a 10 layer, a 6 layer, a 4 layer board, then certainly you can make it from China. I know some companies, I will give you their email addresses or their website addresses over there. You can order it, but certainly the cost is more, and if you are going to just make one piece, the cost is going to be higher. Now where are these PCB used when I'm talking about a 30 layer? Now you know, in space, whenever you have to transfer some payload from some satellite or somewhere, that payload has a cost, because if you increase the weight, you have a lot of amount of, and you have more volumetric size of that weight over there, then certainly you have a lot of fuel to be expended over there, because you have to escape the Earth's velocity and Earth's gravitational field. So you have to reduce down the size. So in space you have to have more layers. The size is small, and 30 layers are used over there. I know from Keepout Laboratories, I know some person over there, they know that our missile technology, they are using something like 10 or 12 layer boards over there. They are developing that boards over there. Again, that technology is not their built one, they have taken it from China. So certainly they are dependent again on the China for the tools and all that equipment over there. But as far as the design is concerned, you are totally free, you can design it. So this software is again a cracked version over there. The original software price, I guess, is more than, I guess, $2,000 or $3,000 per individual piece. So we have this cracked version, and if you are working somewhere for some multinational organization, then certainly they will ask you the price of this licensed version over there. Okay, coming back to this Altium software, as I told you, this setup is not that big. I hope everyone has installed it. 2.47 GB is the software, and I have also shared the link of this software. I'm talking about the libraries, and these libraries are the ones which are developed by me, or I have collected them over the last 15-16 years, and there are some built-in libraries which are available in this folder. You can download this folder. I have given this link in the CR's group. I guess CR has shared with you, and this is the libraries which we will be using in the 3 or 4 experiments or 5 experiments which are PCB design based over there. And you can see by the name of them, you have an LED which we are going to use today as well. You have the push button, you have the PCB block connector over here. This is the PCB block connector over there. Then you can see over here the RGB dot matrix, that is the red, green, blue dot matrix, and then you have the yellow or green dot matrix. So these are all PCB footprint file. By footprint I mean that whenever you are designing a PCB over there, you should know that this IC has what design, what are the pads on which it has to be focused over there. So this footprint or that PCB library file, the extension of this file, if I can just show you, the extension of this one is approximately PCB LIB over there. One thing very important, I don't know how many of you will be working and sharing some, but on this one, whenever you are making a PCB file, please do not share it on your WhatsApp. Always zip it and share it. If you are even sharing with someone else, either because the WhatsApp takes it as a doc file and converts it into a Windows Word doc file. So don't do that without any sharing. But I guess you don't need to share. Before I start the software, one thing very important, you are doing a lot of experiments in this software, and if I'm talking about the experiment over there, these are some of the rules which you have to follow over there. And if I just go through this one, some default values which I will be going on through as this lab today progresses. I will talk about this one little later. Now, in case you are not following these guidelines, your PCB will not be approved and it will not be manufactured, and certainly it will not be solderable. So these rules which I have listed over there, they are very important. I have shared with your CR as well, and I hope I will place them on the website as well. Now, very much things which are very much in this over here. Any experiment or PCB doc file, whichever you are submitting, that has to have your group name, your name, that is the first name. Now, if anyone's name is Ataullah Isa Khan Khail, we don't need to write the whole full name, only the first name initials are enough. So if you are Bilal or Ahmed or whatever, you can just write your full name over there, and that is enough over there. Secondly, the experiment number, that is experiment hash mark 6 over there, it also be done. Why they are mirrored, I will tell you in the later stage over there. Then secondly, there has to be a margin, which means that this margin, when this PCB over there, which I have in my hand at present, this margin which is cutting by the manufacturer and giving it to you, this cutting has to be told by you, and that layer is called as Keepout Layer. As the name suggests, that beyond this layer is going to be no track, nothing beyond that. So that track has to be added over there. I will tell you how you are actually going to. The fifth thing, which is very important, you are always going to put standard dimensions on your PCB. And what I mean by that, if I can show you a little copy of one experiment, I have this experiment 6. So you have to put this dimension over there, as you can see. Now, why I'm asking you to put this dimension, certainly the manufacturer is going to delete it, it's not going to make it. But when this design will be submitted to me and I am going to check it over there, I am certainly going to have a check on, maybe not the first experiment, but from second or third experiment, size will be a very important constraint. Because larger the size, the longer is the, higher is the cost of your PCB, and certainly the material cost is also more. So this is very important that your sizes are constrained, and this is your duty that you have to add this dimension, because if you submit your PCB without those dimensions, I'm not going to check it. And this is very important that both the dimensions, the length and the width, they both are done by you. And as soon as I open your design, whatever that design is, experiment number 6, 7, whatever, I know what is the size and I can just. And secondly, and very importantly, if you are not going to follow these 5 rules, you are going to have a reduction of 0.5 marks on each submission. Okay, this is very crucial. Any PCB design without these 5 attributes is not going to be accepted, not going to be approved, and you are going to lose 0.5 marks. Each PCB, whenever it's going to come to me and I am going to actually check it by some rules, certainly they are going to be out of 10 marks. And very importantly, as I have told you previously, in case of cheating found in any design with any other student or the both students who have cheated or from where you have cheated, will be awarded F grade to both students. And this is very strict. Even if you have done experiment number 1, 2, 3, 4, 5 with utmost good and you have got 10 out of 10 marks, you do cheating, you will be caught, you're straight away F. I will not see any previous grade or whatever. So this is very important, and do that. And that's why please do not share your file. the last 3 or 4 years I have seen students, वो आते मेरे पास, सर वो मुझसे मांग रहा था, उसको समझ नहीं आ रही थी, तो मैंने अपनी फाइल उसको भेज दी, उसने मेरे से प्रॉमिस किया था कि सर वो अपनी बनाएगा, मेरे से सिर्फ देखेगा. The point is, he starts working or she starts working on your file, you are also doing, that person is also doing. So please don't do that. Do not share your file with anyone else. Only submit it at that proper link or location which I am going to tell you as the time goes on. Secondly, or thirdly actually, secondly and firstly are more now. PCB will not be ordered by any student unless it is approved clearly. आपने कोई PCB design मुझे submit किया, you have submitted it. Unless and until I give a tag of approved on it, you are not going to order it. This is very much important. Why? Because there are errors in your PCB. You have to rectify it, and every design will be coming. Like for experiment number 1, I have 2 to 3 revisions, which means the first submission will be coming to me. I will mark it and then I will return it back that okay, these are the problems, insisted it, you have to return it back. I will give a deadline of 1 day or 12 hours or whatever. That design will come back to me, and if it again has error, then I will ask you to submit it again by revision 2. So this process will continue to go on for experiment number 1, 2 and 3. Then afterwards, maybe then you have become professionals and you know how a PCB is designed, then you still require approval, but this revision process will be not there, because that takes a lot amount of time, and your time also and my time also. So please, this is very important. Unless and until your PCB is ordered, or sorry, approved, you're not going to order it. And please, at the end of the lab or anywhere, don't come to me saying me that okay sir, वो हमने सोचा था कि आप अप्रूव तो कर ही देंगे, हमने गलतियां निकाल दी थी, तो हमने पहले ही ऑर्डर कर दी क्योंकि बनने में 3 दिन लगने थे या 2 दिन लगने थे. Don't do that, please. Don't do that. You will waste your money also on the ordering and getting that manufactured, and you are also going to have some negative credit for that one also. So this is very, very important. And nextly, very importantly, whenever you are submitting a design to me, I have the schematic with me. I am having 170 or 180 plus students in this lab. I am going to check each and every design, like there are approximately 1, 2, 3, 4, 5, 6. So just multiply it by 180 by 6, and there are going to be 1 or 2, 3 revisions. I cannot check each and every PCB design on schematic scale. This is very important. कि आपने A को A के साथ जोड़ा है, सेगमेंट B के B के साथ जोड़ा है या नहीं जोड़ा, ये आपकी जिम्मेदारी है. What I am actually going to say it, if I have a PCB design in front of you, supposedly this one or actually this one, I am just going to see that okay, the pad sizes are according to the rules, the tracks are not very close, the names, your name, string or whatever, that your group name, your section name, experiment number, they are there, or any other big problems are not there. मैं individually हर student के schematic design को नहीं देख सकता. So this is very much your responsibility that you are actually going to see what is your schematic. If you do a mistake here, this is not repairable. This is very important. In a Vero board, whenever you had a Vero board with you, you had the advantage that you could actually make it desolder and then put it back. But in a PCB, the tracks are permanent. You can't do anything unless and until, yes, you can take a hole and then you can bring a wire from one point to another, but that will make the PCB non-aesthetically over there and it's going to be a messy structure. So please have the responsibility of your schematic. This is very important. If you are not going to follow the schematic, then certainly you are going to have a problem, and that will be totally your responsibility that your PCB is not working. Okay? So this is very. As far as the experiments are concerned, they are going to be experiment number 6, which is actually going to be the PCB design of experiment number 1. It's a single layer PCB, just something like this. As you can see, on the top side you have the ICs over there, or the dot matrix over there. It's actually yellow dot matrix, and over here you have this the component. This is an SMD PCB actually coming on from experiment number, if I'm not wrong, experiment number 9 or 10 actually. This is that experiment PCB over there, and you can see the components over there. So this is a single layer PCB, and 3 single layer PCBs are going to be formed in experiment number 6, 7, 8, and then 9, 10, 11. They are actually going to be double layer. One is going to be simple through hole components. The other one is going to be something like this, having SMD components over there. So you can see the SMD components over there. So these are some experiments over there which you have to do, and they are just a repetition of what you have done on your Vero board scale. The only one experiment new added over there is experiment number 11, which is a PCB design of an IoT based relay. I don't know how many of you are familiar with the term IoT, which stands for Internet of Things. You can actually control any device or from remotely or from internet or anywhere. So we will design a simple PCB. I'm not going to talk on the firmware version or the code and all that. If anyone is interested, I can share that with you. But overall, we will design a board which has 7 or 8 relays, and that 7 or 8 relays can actually control any of the lights or fans or whatever devices you want to control over there. So that board will be helpful for you when you actually reach on for your 5th semester of microprocessor systems course. Then you can use that board for any of your projects, or even at your home you want to have some remote control for your lights or fans in your room or whatever. So this experiment will be helpful for you at that time. So these are all some of the rules. I have shared these rules with your CR. I guess please go through them stringently. These are very, very important. Coming back to the software over there, I am going to start with a new file. Okay, I will come to this final version afterwards, but this is your file. As soon as you click on file, you click on new, and here you can have the PCB file made first. Now one thing very important, this software has this advantage that in this software you can first of all make a schematic, and the software is actually going to convert that into PCB itself. But there is a glitch over there. The glitch is this, that if you are using a 74SC4511, a 7 segment, or some resistor or some MAX7219 IC, that IC model has to be inside this Altium software so that its schematic can be made. Now getting that model inside the software is a little tricky part, and you won't get all of the components easily, because manufacturers, they can give you the hardware, but they will not give you the software model of anything, because with that software model, you know what is inside that IC, you know how many gates are inside, you know how many NAND gates, AND gates are inside. So they never give that software part. Yes, if it's a it's a common IC available on the last 20-30 years, maybe they can give it, but this schematic is a little problematic. As you will go on in your 3rd or final year, you will understand that having a schematic is much easy if you have the models with you, and then the software has the ability from the schematic, it can convert it into a PCB very easily. But here in this lab, since we are not going with the schematic part, we are straight away going for the PCB design directly over there, and this software, you are going to tell that which component is going to be connected with which. Just like this one, as you can see, I just told you over here in this one, if I can open this one, actually not this one. Okay, you can see over there these white color thin lines. These are actually nets or nodes, and I have told them that they are connected. Like for example, you can see over there that this pin number F is connected with this resistor, and there is a fictitious line over there which is telling me, and I have told this one. We are just going to show that on over here on your file as well. So this is something which I am actually going to make you over here today. So coming back to your file over there, when you have actually clicked on file, you have new, and you are going to click on this PCB file over here. Now as soon as you click on this PCB file, you will have this black color area, and this is the design area on which you are actually going to have your PCB design over there. Next thing, when you have this software fresh installed, there are no libraries inside it. You have to install libraries yourself, and these libraries will be coming on from this folder which I have been shared again on the Google Drive. You can download it. The libraries inside this PCB footprint folder, they are the default ones. You can download it and you can add them together, and these ones which I have shared extra over here, these ones I have collected over the years, or I have made this PCB footprints myself. As this course progresses, maybe we will have a 15-20 minute session for how to make a model as well, or how to make a footprint model as well. We will talk about that one, as maybe for a relay we can ask you to make it, but otherwise these are the libraries over there which you are going to use in the first 3 or 4 experiments very easily. Now coming back to the software over there, still the software is empty. As soon as the software is open, you don't have any libraries added over there. I just deleted them before this class was starting, so because I have made this PCB over there freely. Now when I have to first of all add any component over there, you have to go on to the place component. This is very important. As soon as you click on this place component, you are being told that there are no sources found. This is please log in. Now this is actually a crack version. You cannot log in on the Altium server, so you have to go on with the local install over here, and as soon as you click it, you are going to have this advanced file based libraries over here. I can just maximize it over there, and I have to add over here all the libraries which I want. Now straight away you have this installed library. I will click on on this install, and as soon as this goes on, I can go on towards my Altium extra libraries. I want to add the first default libraries. Now if you see in this folder, if you just go through them, there are a lot amount of libraries over there. One is CAN, one is Capacitor Electrolytic. You can see a lot amount of other names which are little dissimilar with you, but the one which is very much important is this library, which is dual inline package. Now this is the same library that is housing the dual inline dip packaging which we have been using up till now, and by dual inline packaging is this packaging over there which we have been using for this one or this one. This was a 1, 2, 3 or actually 16 pin dip switch. This was also a 16 pin. This IC was, I guess, 18 pin if I'm not wrong. So these all footprints are available in this dual inline packaging model. So I need to add them. No need to add selective models over there. Just add all of them. You can do just Control A, but it selects some of the other files as well which are inside it. So I will just deselect them, and I hope they don't actually get added. Even if you add them, no issues with that. I guess this history folder, and I guess I'm just going to check if there are some other. I only want to add Altium PCB library files over there. So I'm just checking on that they are not added. Any other files are not added. I guess they are here, added over here. I hope so. Now there is nothing added. When I've added them, click open, and this will install. It will take some time. You can see I had missed this text file, so this will be okay. And now this is shown over there. I can just close it, and you can see now all these libraries are now available over here, and I can scroll inside this libraries all which I've added. Now each one of them is again a folder, which means supposedly, for example, I go on to that dual inline packaging library. Let me just show. This is dual inline packaging. As soon as I click it, it has a lot amount of options. If you can see, there is a dip 10, there is a dip 14, there is a dip 16, and there is also a dip 18. Now I told you for this type of supply, and you are having this ULN 2803, you will require a dip 18 bit. So if I double click this dip 18 and move my mouse cursor on the black area, you can see that IC footprint over there. Now this is very important. Now here this is on my disposal. As soon as I will click the mouse left button, it will be the right button, it will be placed on it. Now this orientation, if I want to change it, before clicking it, I can just press spacebar, and this can change its orientation. Again I press spacebar, so this is rotating over there. So the orientation, whichever you want, I want this orientation, I have placed it over here. I have another option, I can place another one over there, but I don't need another IC. I can just delete it or press escape over there. That will actually turn off that. So this is that dip switch, and how you can actually zoom in this area. I guess you will have to understand the shortcuts. No need to actually go on this view and then go in the zoom in, zoom out and all that. I guess you can see the shortcuts over there. Now the shortcut which I use mostly, because I have a mouse, and you need a very sensitive mouse for PCB design in this software, you are going to press your control and use your mouse scroll wherever you are going to point it. It's actually going to zoom in. If I want to zoom out, press control and take it out. This will actually zoom out, and this is easy. If I want to zoom in this area, you can see, take the mouse in that area, press control and scroll in. That will actually give you the output over here. Okay, on this software, you can, I just again going back, those who have not followed it, clicking on place, clicking on component, and you have installed all these libraries over there. Now there are some still libraries which are still not installed. I will install them over there. I will click again on this one, file based library searches, and again click on install. And I now want to add the other libraries which I have given you separate from this one, and these are these libraries. 7-segment common anode, you can see the A337J. This is actually an IC being used by my TA in his final year project. You can see some current connectors or LEDs or PCB block connectors, and the yellow dot matrix or the RGB dot mat. I will just add them also here, and now they are added. If I can just scroll down in the bottom, I guess they are added now. So they are now added, and I will just click close on over there. Now all of these libraries, I hope so, they are added over there, and let me just confirm that they are added. Yes, they are added over there. Now I want to work on which experiment. This is very important. I have added all the libraries, and which library use where, this will be. If you want to delete something, just select it and click delete on your press delete on your laptop, keyboard, or whatever you are using. And over here I actually want to have experiment number 1 PCB design. Now this was your first experiment, if you remember, and in this first experiment you had a power supply section, which was this section over there, and you had an IC, you had a 7 segment, and over here you had a transistor, here you had a transistor, some dip switches, this was a 2-bit dip switch, there was a 4-bit dip switch, and some male headers over here which are over here. Now the first thing, I guess the first and most primitive thing in this design is actually the IC, because IC is the main workforce of this one. So I need a dip package, a dual inline packaging, and that is 16 pin. So I will go on my software, again I will go on my place component, and here again I have to select dual inline packaging, and I have to select our dip 16. So dip 16, I will select it, again press the space bar, and I have over here, and I can just right click it and it will be turned off. Now over here, since this is IC 74SC, double click on this designator. What happens, a dialog box on the right opens, and you can write down in this one, this will be 74SC 4511, and you can slide this one inside this one. Now this is for your understanding that you know which IC, or because there can be many ICs in your PCB design, so this is better you name it that which IC is where. Now remember, whenever I am designing this PCB, this is the top view, which means whenever I am holding a PCB in front of me, this is the top view. Any IC which will be placed over there, I am designing this PCB from the top. So when I am designing this from the top over there, this means that the tracks are at the back and the IC is from the front. So the analogy is something like this. Now the second thing over here which I have apart from the IC is the very important thing, resistor. Now how and where these resistors are going to be. But before I go on to the resistor, I guess we should add everything that is required from the dual inline package library. For what I mean by this, since this is a dip switch, and also there is a dip switch over there which is a 4-bit dip switch, and they all are dip packaging. So to add them together, again I will go on place component, and here I will add a dip 8 over there, and I will just scroll down and come down. This will be a dip 8 over there, like this. So this dip 8 is there, and this dip 8 is placed over here like this, and I only need one of it. I now will add another component, dip 4. So that dip 4 will be here, I guess, if I'm not wrong. Yes, this is here, and I will double click it again, and you have it over there. So you have this 3 dip library components, and which are these? This is 74SC 4511, 4-bit dip switch over there, and a 2-bit dip switch over there in this form. Now I can name them also if we wanted. Supposedly this dip switch is being controlling the master control and the dip. So no, I don't need to write it the whole one. I can write it MC, comma, and I can call it DP, which means MC stands for master control, DP stands for the data point over there. I can again select it from the mouse and take it inside the, here this one is the data. I can call it data because this is going to provide the data, the binary data to the IC. Now here you have the 3 dip line packaging from this IC over there. There is nothing else which is available from this dual inline packaging library over there. Now the next thing very important is the resistor. Now to find that resistor, again go on place component, and this time you are going to search for the library that is resistor-axial. Now why this is axial? Because whenever you have a resistor in front of you that is having an axis, that resistor is always having an axis, so this is called coming in the resistor-axial. Now if I click on this axial part, and I will just show you why I'm actually interested in showing you the whole part of this one over there. This is over here, and I want to show the description as well because this is very important over here, and this is my axial. Now if you see the first library, this is 36.5 into 10.5 into 10.5. You can see this is the length, width and height of your resistor which you are using over there. Now the resistances which you are using over there, they are quarter watt resistances. By quarter watt I mean 0.25 watts of resistances, and they can handle the amount of current whichever you are handling. If you are going to handle a 1 watt resistor, maybe a 5 watt resistor, or even more than that, then yes, certainly you will require a larger footprint of size. But normally if you just go on with this 7 cross 2.8 this library, or you want to go with the 8.5 cross 3.3, this is still enough. I will double click it and show you both over there. I will double click it and place over there. You can see the size of that resistor. It's still nominal. And if I want to see another one, let me just show you the other one, which is over here. I will just this is 7.7 cross 2.8, and you can see the size difference. So you can see if you want a smaller footprint, which means whenever you are having this resistor over there, this resistor, you can see whenever you have placed them over here, you have the legs coming out. Okay? If you don't want those legs, then certainly you can use this designator 3. Then the legs all will be inside the hole and you can cut them at the back when you are soldering it. But if you want a little longer patch, then you can use this designator 3, the 10 cross whatever that size was. Okay? So this is very important, that which size you are using, and I hope so you will understand this as you will understand. I want to use this designator 3 size over there, and if you want to again see what footprint is it, double click this footprint and this will straight away go and take you to the footprint, and this is actually 8.5 cross 3.3, you can see, and the lead is approximately, lead dia is 0.7 mm. This is the dia of that axial lead which is inside any resistor. Now I want to change the designator, so I am having in my circuit diagram a lot of resistances. For example, I have 2 resistances over here in the transistor, I have 2 resistances over here in this transistor, I have a resistor with the LED, and I have 7 resistance over there, plus these 4 the pull down resistances. So how many total resistances I have? 7 plus 1 8, 8 plus 4 12, 12 plus 4 almost 16. So just 16 resistances I require. Now how I am actually going to name them, it's very important. This is a very small circuit, naming is not going to be that much crucial, but I will advise you to make a habit, because when you are going to design a very big circuit, then that will be a problem. So first thing first, zoom in inside this one, go on designator 3, and I am going to change it to, supposingly I am going to call it RA. Now what this means, this RA is going to be connected with the A of the IC, which means this is this resistor over there connected with the 7 segment A over there. Similarly, I have to write it B, C, D, E, F, G over there. Now, if you are not going to name them together, this software has one ability. If I'm going to call this R1, I'm going to call this R2, I'm going to call this one R3, R4, and similarly any other resistances. This software can do it yourself. How? Now I don't want to go on place and component and add another one, because that's clicking a little bit more. Just select this footprint, press Ctrl C on your keyboard. This changes your mouse cursor to this dot cross. Select, click on this one, and now just Ctrl V. As soon as you will do it a Ctrl V, you can see another footprint is added, and this time there is an increment of 1. This is RA, this is RA1. So now I want a copy of this one. Supposingly I will select RA1, let me just select RA1, and over here it is RA1, I have selected this RA1, and I have changed this to R1. Now I am going to select this one R1, again Ctrl C, click on this R1. Now when I will place another component over there, supposedly it will automatically change every time to the next iteration. It can go up, but yes, it will not. If I have this RA, it cannot do it RB, RC and all that. That I have to do manually. The software is not having that alphanumeric incrementing itself. So over here, this is the way you can do it. Now since I require approximately R3, I have this R4, I have this R5, I have this R6, and I have this R7, I have this R8 over there, and since I require RA, RB, so for that purpose I will have to actually do it manually. This is RA1 or RB, this is RAC, RAD, actually this is RA over here, and like this, and I will just place it over there. Now this is going to be a little difficult thing to edit it every time, but remember, for bigger circuits this is going to be a big problem wherever you are actually going to work on this one. Sorry, on this one, this is RA, and this is RC, and this is your RD. I will just change it over there. I'm just doing it over there, otherwise I can go on and have it RE, and this is RF. You have to double click it. This is very important. In the previous Altium version, when you were having Altium 16, whenever you double clicked a footprint, a new dialog box was opened. But this time this is not a new dialog box. This actually comes from the right hand side as the box over there. So you can see over there that I can just move this in this arena. Achha, instead of your control and this scroll button, there is another way you can zoom it inside one area, and that button is over here in this region. You can set a fit specified area. As soon as you will click it, the mouse cursor changes. You can draw any square or rectangle and this will zoom it inside that area. If you are working in that area, you can do that, or you can use that cursor and the scroll button over there. And the last one, which I left it at that point, this is your RG. So this is your RG. Now, when I have placed all these resistances, I hope they are 16 number. We will do if it's not there. You can see these R2 and R3, they are turned green. Why they have turned green? They have turned green because they are very close to each other, and the software is telling me that when you are going to physically place these resistances over there, they are actually going to touch each other. So the clearance between these two resistances are not according to the rules which you have set. Now if you just select it, you can use the mouse as well, and I will strongly advise you, if you are going to design this PCB in your future, I will advise you to have a very sensitive mouse on your control, because from a very bad mouse control, the tolerance level, the software is going to be a very bad experience then. Now you can do that without your mouse as well. Have your control key over there. You can move it by control key, selecting, pressing the control key. You can use your arrow keys and you can move it up and down. Now you can see I am moving it up and down. Now it is within the two limits over there, and now the green color violation has gone. Now if it was green color violation, let's just see. If I make it down, now this is a violation. Now which violation is it? For that purpose, click on this R2 over there, select it, right click it, and go on violations. As soon as you click on this violation, you can see there is written component clearance constraint. Component clearance constraint, which means that you have a component clearance constraint, which means that the two components R2 and R3, they are so close that the clearance is not being followed over there. So this is your R2. Again, I will just use your control key pressed and your cursor keys or your arrow keys, and you can have it placed. So all the resistances are, I guess, placed. Now I will just make it something like this over there. Now the next thing, apart from the resistance, what is that next thing? The next thing is the 7 segment, because that's very important. That's actually it has to display the 7 segment over there. Now this library is going to be available. I will just go on place, again I will go on component, and this time I will go on dip LED display. Dip LED display, I hope this is there, dip LED display, and it has almost all of the 7 segments. Now the 7 segment which you were using in this lab up till now, I hope I have something over here, they were of some specific size. They were of some specific size. That size, if I am not wrong, is available over here. This is LED dip 14.27 and this one. I hope so. I have not done something wrong. Yes, 10 leads. You can see this is written LED 7 segment display. 14.27 is the height over here of this one. Right hand over there. Why? Because if you see very closely on your 7 segment, it's tilted writing. Okay, it's tilted writing, so you are giving it a right hand over there. 10 leads and row spacing is over here. If you can just over there, it's not actually coming out. So I will just check on. I will just double click it and place it over there, and I hope so. This is exactly what I want over there. I will just zoom in, and I hope so you can see this is exactly the same footprint which I require over there. For just to verify what I have done over there, I will just double click the one which I have used previously, and I will double click it, and you can see this is the same footprint, 7 segment display, row spacing this one, and pitch this one. So this is this library. Now you will have to actually remember this thing, because all other 7 segments which are available in this library, again if you go on component, this library is selected. For example, if I want to select any other, just for example sake, I want to actually use a larger one. Supposingly, maybe I have some, yes, there is a 20.32. let's supposingly I want to have this one. Now this is a little different. You can see over here, this is a little different 7 segment over there as compared to the other one. So please remember what you have to use. Any experiment in this lab, you're always using this one, unless and otherwise stated, or any project or whatever. So this is very important that you are only using this 7 segment. I only require one of this 7 segments, so I have placed it over there. The next thing I require apart from that 7 segment, I have the IC, I have the dip switches, I have the resistors over there. The next thing is the transistor. Okay, I will come on the power supply section at the end. The other thing is the transistor. Now this transistor is a 2N3904 transistor, and this transistor is going to be available in the library which I have shared with you additionally. So this will be place component, and from here there is only one library and it has only one component. If you just scroll down, you will find out transistor TO92.PCB library. Now if you remember your 2N3904 data sheet, this is the same TO92 packaging, and if you click it, there is only one inside it. There is only one in transistor, and if you double click it, I will have only one. Since I require 2 transistors, I will just place 2 of them and click escape. Okay, so now I have 2 transistors. I can name them over here as I want. Supposedly I want to call it supposedly master control. This is my master control over there. This one is my, you can call it the DP control, since this is going to control the data point or the decimal point over there. You can see when I zoom it inside it, it has a semicircle over there. It's easily telling you that this is the collector, base, emitter. Again, this is the top view, but how you are actually going to place it over there, this is very important. Your transistor, when you are actually physically going to make this over there. Now the next thing apart from this transistor, you have all the resistance, you all have this one. The next thing is the male header. Male headers are very important. This 2-pin here, 2-pin here, and 4-pin here. This library is going to be available in place, again going on component, and this time you have to select a miscellaneous connector library. Again, they are alphabetically arranged if you are taking it from one folder. This is very important, not the other ones, because the my are different over there. This is miscellaneous connector PCB dot. Now here you will find out all the connectors which you require, and the one which I require, if I just go back on your diagram, is a 2-pin here. I need a 2-pin here, and I need a 4-pin here. If I go back on your software and just scroll down, you can see over there is written HDR 1x12, 1x12 or 1x12, but I require something 1x4. Now what is 1x4? If I double click this one and bring it here, you can see this is a 1x4 male header. You can see 4 pins, you can see 4 pads, and this is going to be that markation or the outer boundary of your male header. You have this male header in front of you. This is your male header, and you can see the black color boundary is that yellow color boundary over there on your PCB. Whenever you are making, either you are making it on this Vero board, just like this one, you have this Vero board over there, or either anywhere you have the male headers over there. I guess there is only one male header here, so you have this male header. So you want a 8-pin, you can just again go on place, click on component, and just scroll down. You will find out HDR 1x8, and you can see now you have 1x8 pin over there. But I don't need a 1x8, so I will just select it and delete it. I only want a 4-pin and 2-pin over there. So I will only have, again go on place component, and I need to find out 1x2. Where is my 1x2? This is my 1x2. And I require 2 of these, or I can only use one of them. If you remember your circuit diagram, I told you that this can be 1 pin, this can be 1 pin, or you can combine them into one male header of 2 pins over there. So that will be easy. So I'm only going to use this 1-pin male header, and I'm just going to call this one, this is the master control, comma DP. So I have just called it master control, comma DP, like this one. Now this master control and DP is done, and this one is the data. I will just double click again, and this is my data. So now the main headers are also there. Now I have placed all this component haphazardly. Now how you are actually going to connect them and all that, that will come when I have placed all the components. Now let's just check which is remaining. I have to still add block connectors. This is the input block connector, this is the output block connector, and then I have to go on towards the power supply section over there. First of all, the block connector. Now here, if you remember in your Vero board, I told you at that time that whenever you were having a Vero board, you were using 2 block connectors over there. One was the input, the other one was the ground over there. Now I told you at that time, if any one of you can want to use, since there are 2 pins in each block connector, if you want to use one as input, the other one as ground, totally okay. You will just have to make some jumper wires over there. So in our PCB, since PCB is on our working over our design, so I am only going to use 1 block connector over there. 1 pin will be VC or the input, the other pin would be the ground. So that 1 block connector is going to come from place component, and this time I am going to use my PCB block connector, which I have designed it. Sadly, it's not available on the front over there. So if you see over there, PCB block connector 2, please don't use that PCB block connector. I guess I will delete it from that Google link. Only use PCB block connector 2, and if you double click it, now you can see, if I can just zoom it out over there, this is my PCB block connector. Now if you see very closely over there, this PCB block connector has this yellow color points over there, or half of that circle or whatever. Now why I have done it, because in every block connector, if you remember, there was a space from where the wires can enter. And I told you specifically that whenever you are doing it on a wire board, the wire part should be out of it, because then you can insert the wire over there. So this yellow ones are actually identifying that the wires are going to come out from there. So this block connector is going to be placed on the PCB in such a way that this yellow ends should be on the edge of your PCB. Otherwise, if they are placed different than this one, which means they are upside down, then the PCB is going to be having the wires inside. They should be coming in from the outside. So these yellow ones are very important, and they are made in such a way, if you just see very closely, if I select it and I want to place another one like this. Now they are made in such a way that if I want to actually add two of them, so this edging is there. And if you see very closely on your block connector, I hope everyone can see those, especially those who have this green color ones, there is a notch over there, and that notch can actually add 2 plus 2 plus 2 plus 2, so you can have a series of block connectors added. So these notches over there, this notch, and this notch, they are actually telling you, and I can bring it as close as possible, for example, but not more than this. I guess this is the minimum clearance I can have. So this way I have 2 block connectors with added together. Maybe in some of your any other lab or maybe any other project you will require to have all block connectors in series, then you will require this block connector. I can change this one, the designator over there, the designator I can call it the input, comma, ground over there, and this is my input over there. So I have this input and ground, and this is like this. Now coming to the other thing, the power supply section. I have a regulator. Now maybe for experiment number 1, heatsink is not required, but it's compulsory over there to use a regulator with a heatsink, and also the capacitor over there. So heatsink is always a must, and in any of the power supply which you are going to design, please always use this place component, and over here go on this umar.pcb library. I guess some student renamed it, that's why I have it named by Umar. So if you just go in this Umar library, you will find out LM317 with heatsink. Now LM317 is exactly brother of 7805, but it's adjustable voltage regulator. So if I just double click it, you can see what is it. You can see this is again that 3-pin voltage regulator, and at the back you have the heatsink. I don't know, I have some heatsink enabled over here or not. I don't have any heatsink with me at present, but anyway, you can see over here this region over there, this region, I have to add. So this region over there where my mouse is, and this notch. Now if you remember on your Vero board, whenever you are putting that regulator, and whenever you are putting that regulator and you are putting a heatsink, I asked you at that time कि जो notch निकल रही थी heatsink के नीचे से वो आपने काटनी है, because that cannot fit inside it. Now this time on a PCB, you are not going to take it out, you are going to let it go inside this hole at this point. So this hole is actually going to keep that heatsink straight on the PCB over there. So this is that 7805 regulator. This one is your input, this one is your ground, this one is your output, and you can see the margins over there. So I can just click on this designator over there, and I can call it 7805 over there. So you have the 7805 over here, the regulator. Coming back to the other diagram, what I have now remaining, I want to add an LED. Resistor is already added over there. I only have to add capacitor and the LED over there. So again, going on place, component, and this time I will go scroll on to my LEDs over there. I guess there is an LED 5mm over there. Our LEDs are 5mm. There is only one of them, and you can see this is my LED added over there. So I can just double click it again and name it LED over there. Have this habit of always changing the name of the designator, because in bigger circuits, especially something like experiment number 5, 6 to go on, otherwise the circuit is going to get complex and it will be very difficult for you to debug your errors if you are going to not name it. Just imagine if all of these components are designated at designator 1, 2, 3, 4, 5, 6, 7, it's going to be very, very difficult for you to make it. Now, the last thing to add is the capacitor, and that library is going to be available by default inside it, but by addition, if I just scroll up on this one, I have the capacitor over there. Let me just scroll on to see. They are all arranged alphabetically. So you can see over there capacitor, electrolytic over there. These are electrolytic capacitors. So I have electrolytic ring over there, and if I am not wrong, I will just scroll out. Actually, my screen is limited because of this projector connected, so that's why. Okay, I have this one 16 cross 30. You can see the body of the capacitor. Now, the capacitor which you are using over there, I can show you over there, the 16 cross 30 mm. 30 mm is the height, 16 is the dia over there. Now, I am just using a very smallest one, so I will just click on this one. You can see this is a very big capacitor. I don't need something like this. So you will have to go again on component, and let me just verify the one which I have used last time. I guess this was the capacitor. This was available in the capacitor electrolytic radial over there. So this one was the capacitor. I will just go back on your file. Place component capacitor electrolytic radial, actually, sorry. Where is my radial? Okay, radial cylinder. Yes, this one is. And here I will add the capacitor which I require over here. You can see they are very small capacitors also, 1.7 cross 3.18. There is also one over there. The one which I am actually going to use is something like this. This is still enough for your case, and you can see this capacitor serves the purpose. The capacitor which you have brought from Hall Road, please measure their height and the dia. The height is not that much important because on the PCB they are going to stand up front, but as far as the dia is concerned, measure the dia. Find out where they are going to be, because many of you must have bought something different. So see that capacitor from this library. The library remains the same, that is capacitor polar radial cylinder.pcb library. So I need two of these capacitors over there because I have 47 microfarad and 4.7 microfarad, and I can change these names again to 47 microfarad, and here this will be changed to 4.7 microfarad over there. You can see the positive polarity also, the negative polarity over there. Now all the components are added almost. I guess I have not missed anything, I hope so, and everything is there. Now how I am actually going to tell the software that which is going to be connected with which pin. Now, okay, the same diagram, if you remember, I showed you this diagram just now, and now the connection part. Now if you just zoom in this diagram, what we have done on each one of these pins, you can see with the blue color, the light blue color, what I have written over there. These are the names of the nodes which I am going to define in this software. I guess every one of you has an idea what is a node from your circuit analysis course. Now this pin number E, or pin, sorry, this is E, yes, E is connected with this resistor. So I am going to have this discrete node, and this node is going to be called as E_IC. Again D_IC for this one, C_IC, and so on. Then F, G, A, B, C, D, E, these are the again nodes, and they will be connected to G, F, A, B. The wires are not shown over there. Similarly, I am going to have this common collector over there. Then I have this 33 ohm resistor. Then there is going to be a node master_C, which means master control _ collector. These are all the names of the nodes which are technically called in our software as netlist. Now what I mean by netlist? Netlist are the nodes which are inside this diagram, and you have named them over there according to your understanding. Now I will strictly advise you not to name any of the netlist as 1, 2, 3, 4, 5, 6, 7, 8, 9. Why? Because for maybe for small circuitry this will work fine, but when you are going to go for debugging of your any PCB, it will be very difficult. So always make the names of your netlist according to your easiness and your understanding. So you can see over there, this pin is D1, D2, VCC, because pin number 3 and 4, if you remember, they were connected to VCC. Pin number 5 was connected to ground. So no need of naming them those nets. They are already going to be connected to VCC, ground, D3, D0, and ground. And then I have this the dip switch. Then I have the 1 kilo ohm resistor, and then I have this male header and the ground. So I have to name all these netlist over there, and how to name that netlist. Now for this purpose, go on design, click on netlist over there. Netlist are, again I told you, are the names of the nodes over there. Click on edit nets over there, and here the list is empty because up till now I have not named anything. So again click on add. Now this time it's going to ask you the name of that net. So I will first of all add A. You can see the A is added. Now you can do this with your keyboard easily, don't need to use your mouse. Click enter B, click enter C, click enter D, click enter E, F and G. So you have named 7 netlist over there. Similarly, you want to add another one, A underscore IC, B underscore IC, C underscore IC, and then D underscore IC, E underscore IC, मैंने miss तो नहीं कर दिया कोई, E हो गया, F हो गया, okay, G is remaining, G underscore IC. So now I have added almost 14 netlist over there. Now another netlist or net node, one is VCC 5 volts over here, and I have over here ground. Now apart from that ground and VCC, if I go back on your diagram over there, in this diagram almost everything in this IC is done except your D0, D1, D2, D3. So those are the nets over there. Again I will add them over here, D0, D1, D2 and D3. So as soon as you have written it, now the list is populating itself. Again this is alphabetically arranged. So now you have everything over there. Coming into this section, here the same names are there, same netlist, nothing changed. Coming to the transistor. Now I am only going to add in front of you today one transistor over there. Then one transistor is the master control. Now you can see from the common collector there is a line coming inside the resistor. Now this has to be given a name. I have going to call it CC or common collector. So I will add a net over there and that will be called as CC, calling as, or CC capital. You can use alphabet small or not, totally up to you. So CC common collector over there. Then the next one, if I go back over there, then this pin over there, from this resistor 33 ohms into this collector of the transistor, this is going to be another net. That is going to be called as master underscore C or master underscore collector. So I can name them as over here. This is going to be master underscore collector if you want to call it. I will just going to be having, don't need a very long name because that will be difficult for you to type it down and then again scroll it. So this is master underscore C. I can also use M underscore C. If you are good with abbreviations and understand it, so master underscore is okay. So I will also add master underscore B because that is the base of the transistor. Again also, if I go back on the circuit diagram, the emitter is also there, but emitter is by default grounded, so no need to add that ground or resistor over there. So then I have this base. This is the base or the input from where that master control is going to come, and this will be connected with the dip switch. So I am going to call that one over here as master underscore control. That is one thing, or I can call it just MC over there, which would be up to you. So this is master underscore control. Now then there is one more remaining. I have added all the netlist over there. The only thing remaining is this 330 ohm and the LED connection, this wire. Rest, this is VCC already there. This is ground already there. The only thing remaining is this 330 ohm and the LED, and I can name it, supposedly I can call it LED underscore RES. This is LED actually, resistor. So this is the resistor LED, and the last one is the input, which is going to be connected to your block connector over here. What I mean by this one, because from this input this will be coming in your regulator. From the regulator this will be connected with your ground, and there will be an output of VCC or 5 volt, and that is already defined over there. If you can just see over there, VCC is already defined over there. If you want to call it 5 volt, it's totally up to you. You can change the name and call it 5 volt. It's totally fine with that as well. You can want to use VCC, it's totally up to you. But remember, whenever you are designing it, keep it always the same. Which I mean by that, experiment number 6, we are designing it. If we have used VCC, for experiment number 7, 8 onward, use the same nomenclature. That will be easy for you to actually debug your circuit. Now when you have added all the netlist, now here the difficult part comes. The difficult part is this: you have to take every pad. And what are pads over there? Pads are these pads on which the IC is going to be soldered. Double click each one of these pads and assign that netlist to that pad. What I mean by that? Supposedly if you go back to your IC is somewhat here. Pin number 16 is VCC or 5 volts. Okay? So this means that you have to double click on this pad. This is 16. Double click on this pad, and this is open. And scroll down over there, you will find out net. Here in the netlist, all those netlists are there, and you have to select the 5 volt over here from here, this one. Now what has happened, if you just zoom in this one over here, you can see with the pin number 16, there is a 5 volt also splitter. Now what is the 15th pin? 15th pin over here is F_IC. So this means that on the 15th pin, again double click on this one, you will again find out, you will have to scroll down and go to F_IC, click again anywhere, and you have all it. Now this is the difficult part. This is going to be difficult for you because what you are doing over there, you have to click on each pad and assign that net over there. Similarly, for example, I'm not going to do that in front of you. The file is already there with me, so I will use that. This is the LM7805. This is your input. So I will just double click this one. The dialog box will be open over there. It takes a time depending upon your RAM. Actually, my RAM is at a lower level at present, so it's taking some time. So here this will be input. So I will just click on input. Now, as soon as I have clicked on input, the second one is the ground. So this is the ground. I will just scroll down again. This is the, oh sorry, the wrong function. This is ground. And if I double click on the third one, this is my, sorry, this is your VCC. So this will be your 5 volts. Where is my 5 volt? Actually, so now as soon as I have clicked this one, see this one, what has happened? There is now a fictitious line from your output of your regulator to the VCC over here. So you are going to assign each of these pads that netlist. So you can see this is also 5 volts over here, and this is also 5 volts over there. Now, since this IC has a ground at this pin, so this means this is a ground at this pin. So this will be over here, ground over here. And as soon as I will click it, you can see now that line also connecting the two. So when you will connect all the netlist, your circuit is going to be. Now, this is the hard part over there because you are not designing the schematics. If you would have designed the schematic first by using the library, then this netlist would have been done by the software. Since you are not having that schematic, you are actually going to do it manually over there. Now I am going to go towards my file in which I have already defined all the netlist. I will just delete this margins over there for your understanding, and now I have added all the netlist over there as per my diagram. And you can see the netlist over there is like this over there, which I have used over there. Now, how I have placed this ICs and all that, where to place it where. Now this will come with experience, and when you will reach experiment number 7, 8, 9, you will understand it. Now, for example, these 7 resistances, which are actually A, B, C, D or GF, they are placed on top of this IC Y. They are placed on top of this IC because just with VCC there is F, there is G, A, B, C, D, E. So I have all the 7 resistances just on top because the tracks can be placed easily. So you have this R1 to R7 placed over there. So you have this one, and then I have placed the 7 segment just on top of it. Why? Because the wires are going to come from this end and they are going to connect with the 7 segment pads over there. So this 7 segment pads. Now before I proceed on further and tell you all the nets over there, one thing which I missed over there, if I go back on over there, if you see very closely over there, the pads are not of your uniform width or size. What I mean by this, if you click on this over there and you click on this pad, I hope so the component box opens. The component box should open. Okay. And you scroll down a little bit, you can see the size over there. The size over there, shape is round. This is round, and over here inside this lab, whatever experiments you are doing, it will be always round over there. You are not going to use a rectangular, you are not going to use an octagon, or you are not even going to use a rounded rectangle or whatever. Every time almost it will be round conductor. Now here the size written in X and Y is 85 mils. Now this mils is a unit of 1/100 of an inch. Now this is not a very standard unit. You are not using this every time whenever you are working around. You are always using millimeters, centimeters or something like that. To change it to millimeter, you will click on your view and click on toggle unit. Now as soon as I will click this toggle unit, what has happened now, if I again double click any of the pad, the dialog box opens over there, and now you can see the pad size is 2.159, 2.159. And now here comes the point. If you remember in the start, I told you that there were some default values over there. Default values, the pad size always have to be 2 mm cross 2 mm. No PCB is going to be approved or going to be ordered by you unless and until the pad size is 2 mm. Now 2 mm size may be a little larger for you, but since you are amateurs and you are going to do a soldering on PCB for the very first time, so 2 mm is the standard size for you at present. Maybe when you pass out from this lab and you go on further, then you can reduce down the size to. Okay, so we were doing this, I told you that you can add these nets over there, and you can add all the nets which we have defined over there. The nets can be based on your instincts, whatever you want to call them. I showed you this diagram where F_IC, E_IC, or whatever, D0, D1, D2, D3, or transistors, or whatever, you can name them according to your connect. The difficult part is to actually double click on each pad and then do it. Now the problem over here in this diagram, if you can see over there, that the pads are not equally same size. And I told you that there is a threshold. I told you that the pads have to be 2 mm cross 2 mm and the whole size has to be. Now this is uniform and it will remain the same at least for the first 4 PCB designs over there. For SMD we will change a little bit over there, but otherwise for first 3 or 4 experiments this attributes will remain the same. The first thing is the pad, then there is a via, and then they are talking. First of all, the pad. If you see very closely over here, this pad, I told you when you double click this pad, the pad size comes out to be 2.159 over there and over there. Now, and then if I just double click this one, the pad size comes out to be 1.5 cross 1.5. Now they are not equally same. So what I am going to do now, if you want to change all the pads over there, each one of them double clicking it, it's a very difficult task. So what I am going to do, I am going to go on view, go on the panel and open PCB filter. Now as the name suggests, it's going to filter out whatever component you want to select. For example, I will click on the builder. Now this is just like a coding language. This is actually going to do it just like you do it in your Python or any other language course which you are reading. Click on this one, click on object kind is, and click over here for this one and select wherever there is pad. Now what it will do, you can see the code is pad, which means it is going to select all the pads, click on OK and click apply. As soon as I will click this apply, you can see now what has happened. The only pads are selected. All the other components are not selected or they are deselected over there. So now if I want to actually find out, supposingly this is my properties, I have just opened it and I will again select all, and now you can see, okay, I have this one. The nets don't change this net because every pad has a different net and you have defined it over there. The only thing that you have to change is either the shape. You can change the shape to round, so all the pads will now be round. Then the X size, here change it to mm, use the smaller one, and this is 2 mm there. Then just click anywhere on the board and now delete this is pad, again apply all, come back to this one, and now all the pads are 2 mm. Okay, now you have this one and I click this apply to all, have this deleted. So now you have all the pads of 2 mm size. You can just double click anyone and verify that they are 2 mm. Just do it and you can scroll down again, down, and you can see this is 2 mm cross 2 mm and the whole size is over here 1 mm. I actually did not change the whole size. I will just change it again. Again go on object kind is, and object kind is the selection again here is pad. Click on OK, click on apply all, and you have the pad selected, and I will just scroll down over here and the whole size 0.85 mm. So now all the whole sizes are equal to 0.85 as you can see. So all pads are 2 mm, all pads are having a hole size 0.285 mm. Now when this is done, the first rule, please no talking, the pads are there, this first rule is always there, done. The second rule is a via. Now why is a via used? Now if I go back on the first diagram or the first file on which all the nets are connected, and I guess I was telling you that on the top of this IC you have this 7 resistances arranged, and then you have this 7 segment arranged over there. The common cathode is also connected, F, G, A, B, C, D, they all are connected over there. Now see what I am going to do over there. When I am going to place a track, now this software has 2 options. One is auto route, which means you have told the software which nets are which, and it will do it yourself. Now the second way is manual routing, in which you are going to put the tracks yourself. For tracks, when you have done it, go on place, click on track. You can do this by Control W as well, so you can just use the shortcuts as well. As soon as you will click track, now you have the cursor change, zoom it inside it by your control and your scroll key, and now if you see very closely, this is connected with this one, so I can now connect from here and I can have it the blue color track like this. Now this is manual routing. Now before this manual routing is being done, one thing you have to change, because this is an old file. Whenever you are going to have this new file and you have placed everything over there, you have to go on design, go on rules. Now in this rule, in the routing section, in the width, there is written bottom layer and top layer, the routing minimum width, maximum width and preferred width. Now that rule is again going to come over there. The track for this PCB size is 0.8 mm. This is the minimum size you are going to use for your PCB. Now 0.8 mm is the size. So over here, since I am only using a single layer PCB at present, so this one would be 0.8 mm minimum, and I am going to fix both of these, in fact all 3 of these as 0.8, because I don't want any tolerances over there. So a minimum width, maximum, preferred, everything is 0.8. If you want to play it a little, maybe you can keep it 0.79. 0.82 and then change it differently, but here I am using with 0.8. so this will click apply and click OK. Now over here, whenever I am going to again go on place, click on track. Supposedly I want to connect this one with this one, so I will click on the pad, a track will be initiated. Now you can see what has happened. It is top layer, red color, top layer, but I don't want a top layer, I want a bottom layer. So I will click escape, not there, again click this escape. Now what I have selected over here, top layer is selected. I want a bottom layer, so I will select this bottom layer. Now whatever track I will place will be in bottom layer. Bottom layer and top layer is something like this. You have a bottom layer here where the components are placed assembly. The top layer is like this something. So the PCB, when you are holding it in front of you, this is the top layer and this is the bottom layer. But here in this experiment, you are designing a single layer PCB in which the tracks are only on the bottom. So all the experiments which you are going to do in this lab, especially experiment number 6, 7, 8, they all are single layer. So every track will be in bottom, that is blue color. Okay? And red is top layer, that will be done in experiment number 9, 10 and 11 over there. So this blue color is always going to be used over there. Now when I selected bottom layer over there, again click on place track. You can do it by Control W as well. So this changes it, and now this time when it's going to be made, you can see the thickness is 0.8. It is already taken it from the rule, and now you can connect it with this one. So your PCB is having a track like that. Now I am going on the old file which I have over there, and again I can use Control W, and now my cursor changes to that cross, and now I can connect between the 2 points. In fact, no need to actually putting escape, and now you can connect it. Remember one thing, the tracks have to come from the center of your pad. Now when I have placed it, the software has inclined it towards the pad, but it is very close. Now what you can do over there, select this track, use your mouse with the right hand key, keep it away. Because closer they are, the manufacturing process will have some particles over there and it will not be etched over there. So this is very important that your PCB is something like this. And again I can just do some tracking over there. Let me just finish this tracking. So you can see the software does it. Don't worry on the software part. You can do it something like this and like this. and avoid tilted tracks as most as possible. Tilted tracks like this, they are not good. Try to make them a little clearance from this side also, this side also. Otherwise, if they are very close, even when you are going to soldering, you can touch those tracks and you can make a bridge over there very easily. So this is very important that your tracks are like this. Now this was easy. The 7 tracks, they were very easy to connect over there. Now the difficult part is to connect the tracks where there is a crisscross like this, as you can see, because this pad is connected with this pad. This pad is connected with this one. So the problem here occurs that how you are actually going to connect it. Now see this one, you will learn this trick with some time to pass on. But here, click on track. Here, this is straight away connected to this one. So I can do this very easily and I can call it something like this and like this. First track done. Now, the second one, if you can see very closely over there, this one has to be connected to this one. I cannot go from here. But I have a space under my 7 segment and I can bring it like this, because this is still in Vero board this was not available. You had jumper wires, you have to bring that jumper wire from the other way and you have to take it back. Now here one thing more, jiske niche track niche. Similarly like this, when you have a PCB in your hand, you can see the 7 segment or the yellow dot matrix. This is actually a yellow dot matrix placed on this one, and under this yellow dot matrix you can see the track. In Vero board this was not possible. You were having a breadboard style tracks over there. In PCB you can do it very easily over there. You can see it afterwards. Okay, now one thing very important before I proceed on further. This one, if you see very closely, I took this track straight, bended it and then took a 90-degree turn. Never ever make like this. Why? Orthogonal tracks not allowed, which means at 90 degrees to each other. Why? Reason is this, when they will be at 90 degrees to each other, the manufacturer is going to put it inside a ferric chloride or an acidic solution. The edge 90 degrees is going to have more dissolve. The track at that point will become thin. So don't make orthogonal tracks for 90 degrees over there. Always make them a little slanting. Just select this one. I'm just going to select this one, I hope, and drag this one over here, and it's like this over there. So now you have this one track like this. And secondly, very importantly, also do not make it like this. This is very important. Do not make it like this over there, because this is going to be having like this over there. So always make it like this and then bring it down. Similarly, now when this is connected, this pad has to be connected with this pad. So this means very easily, again click place track or Control W. Now there is an ample space in the bottom, so I can take it back down and here, and this is connected over here like that. So now 3 tracks are done. Now still there are some remaining over there. If you can see, this pad is connected with this one. So what I am going to do, again Control W, and I am going to have it something like this, straight up like this, take it up, bring it down, and like this. So this is my track done. Now I have space over there. Let me just take it over there like this, and I can now have it connect like this. So you can see now almost only 2 are remaining. The remaining ones I have done it. They are almost done. But the problem here now is that these 2 cannot be approached from this direction or this direction, but they can be approached here when if I can take this track and gate from the under the resistors, bring it over there like this, like this. So you have a track from this point till this point over there. Similarly, now there is one problem now. This one, there is no space now remaining from where I can take this one. Now you can do it first of all before that one, so it will be easy for you. So now when you have done it, don't not delete it. You can make it stretch and like this one, and similarly this will be a little close, but anyway. So now from Control W again, you can do it like this. Now this will be a little close. I will just change it. You can see the software is actually aligning it, but these are very close, so I am not going to do it. Now here the problem occurs. you have this one on this side, and you cannot, never ever move a track between the pads like this. The distance is so small. Now what you are going to do over here? Here you are going to place a via. Now what is a via? A via is going to be placed, I just clicked on via, and I am going to place a via here, and I am going to place a track from here and here and keep it. Now what is going to be a via here? A via is just going to be a jumper which is just like this as shown over there. You can see the jumper wires which are used on your Vero board. This is the jumper wire. Because it's a single layer PCB, if it was double layer, I could have moved it on a double layer and then bring it back. But this time, these are like something 1, 2, 3, 4, I guess there are 7 or 8 jumper wires. Now the lesser the number of jumper wires which are connected by wires, they are going to be better for you. So you can have it. And again, one thing very important, the size of via has to be also 2 mm. The rule again comes in that apart from the pads, via also same size. Do not have the via over there. How you change the size of that one? You change the size again, go on again view, go on panels, PCB filter, this time again go on builder. You want to select all vias, object kind is from here, select via, is via, apply all, those both are selected. Click on the properties part, and here you can change dia to 2 mm and hole size to 0.85 mm. And I hope they are not changed. So this is your tracks. Now you can see very clearly all the tracks of the 7 segment with the IC, they are complete. Now you can do the remaining ones yourself, but the tricky part is how you are actually going to do the placement. Now if you see very closely, 7805 is placed with this block connector. Now why I have done it? Because this one is going to be the input. So I can now have a track from this point. So this is control W. Let me just have it control W actually. This is place track from here, and I can connect it with this one. Similarly, if I want to have a track connected to the ground, this is ground. I can take it backwards like this, and I can bring it to, now one thing very important, up till now the heatsink was not connected with anything. Now the additional information, whenever there is going to be a regulator on your Vero board or anywhere, this metal part is always connected with the center pin of any regulator, which means it is connected with the ground. So I am using this one, the heatsink will be connected with a screw, so it is going to be a connection, and this is connected with the center pin over there. So now you can see what I have done. I have connected the ground with that center pin over here, and now the third pin is having that VCC or 5 volts available. Now again I can connect it. I have placed these 2 capacitors over here close to each other, so that now I can put a small track like this, and I can have it like this, I can have it like this, and I can connect it like this. So it's totally up to you how you are actually going to place your components. It can be any orientation like this, it can be any orientation which you like or whatever. But you can see they have to be jam-packed. The space should be utilized perfectly. This space, as you can see, is empty still. But now let me go towards the final design which I already have with me. That final design, as you can see, is this one. Now you can see in this one, if I just close it in this one, you can see what I have done. 1, 2, 3, 4, and all these tracks are going towards your 7 segment over there, and from the 7 segment they are taking that power supply over there. Now this one is very close. Do not do this like this. Now why they are very close? Because the software has done this. Okay? Now if I want to ask the software to do it, now I am going to tell you that process also. You have this one, you want to delete everything, supposedly, go on the route, go on unroute all. Everything will be unrouted. Don't do it before saving the file. Save it as a copy and then do it, because otherwise the whole thing is going to be lost. Now when you have done it, now you want the software to do it. It has to auto route it. Now click on route, click on auto route, and click all. Now when you will click all, a dialog box will open in front of you. In this dialog box, if you want to edit the rules first, this will give you that dialog box. Here you have a clearance one over there. In this clearance, you can see the default clearance is 0.254 mm. It's very, very small. One thing you can do, and that is the reason the tracks were very close. Now, since you are doing it as an amateur and you will be soldering it, 0.254 is very, very small. So I am going to make it a little far. I am going to make it like 0.35 or 0.4, so that distance is there. Now this 0.35 will be copied in every place in this table over there, and I will click on apply, and now you can see this has changed from 0.35 in everywhere. Second thing, if you want to change the width, you can change it again over there and click apply again and click OK. Rest of the rules we will talk later on when we do other experiments. Here click on edit layer directions. This is going to tell you either you want to make a 2-layer or a single layer. If you can see over there, for the top layer I have selected not used because I am designing a single layer, and for bottom layer I have asked it to be automatic any direction. By any direction, either it has to go vertically or horizontally, anywhere. So click on OK, and now when you will click route all button, now depending upon your PC power, processing power, it will hang a little if the PCB is large, because it's going to take all those possible permutations and combinations and give you a final PCB design. Here I have this i3 over there. Let's see how much time it takes, because the clearance I have increased to 0.35. So as soon as I will click route 3, you can see now it is doing it. Now you can see over here 48 of 57 connections routed in 5 seconds, 1 contention. It's still doing it. You can see in the background the tracks are changing. The software is itself doing it, and routing finished with 0 contention, which means no error. Every track is connected. You can cross it, and now you can see the tracks. But the software has some glitches still. What is that glitches? You can see this is a waiver track. This type of waiver tracks not allowed. Very important. And secondly, you can see these two tracks, they are very, very close. So try to make them a little far apart like this. By waiver, you can see this is going like this one. Instead of making like this, let me see, you can make it like this, a straight track. Remember, whenever the PCB tracks are wavered, they are going to have parasitic inductance and capacitance effect over there. Maybe for this circuit it can still work because the frequency is not that high. But when you are going to design a circuit, when you reach your third year or final year and you are working at some kilohertz or megahertz frequency, then this wavered tracks will be a mess. And secondly, the manufacturing process, again because of those wavered tracks, are actually going to have the problem of that etching. The tracks can be eroded off. So avoid whenever. First of all, your habit should be not to use auto route. If you are using auto route, even if you auto route it, please do some manual rectification of the track so that they are far. Now see this area. These 3 tracks, they are very close to each other. Okay? If this is going to be made by any manufacturer, they are going to be a problem that these two they connect together. Okay? Because the tolerance level may not be that much good. So this is very important that whenever you have done a manual routing, you can see these ones are okay, the RC capacitors are there, the transistors are there, okay, the resistor is okay, the dip switch is okay, nothing fancy over there, everything is okay. But you can see over there, this one is flowing a little up, so I can make it like this over there. It should not be slanting. Slanting tracks from the pads, not very good. Again, they will create problem. And since I have space over there, I can bring this down. I have space over there. I can again also bring this down over there, like this one. So if you have space, make the track spacey over there. Now, come into the trick card. Here in this PCB, there are no wires. But the one which I designed in front of you, it had a little bit of wires, and I guess I did it for this part. There was one wire. If you can design a PCB without a wire, well and good, no issues. But try not to have more than 4 to 5 wires. This is the maximum limit for experiment number 1. Maybe for experiment number 2, it can be increased, but for experiment number 1, the maximum number of wires is 4 to 5 over there. Less wires, it looks aesthetically bad. This should not be visible. Yeah. statically. It should be simple plain. Okay. Now coming on to the next part, please. Your size of your PCB is going to be decided by your margins. Now how those margins are going to be added together. I will come back to this strings and attached afterwards. On this wire, on this one, click on this one and select Keepout Layer. Select Keepout Layer over here. Go on place and click on line. Not track this time, click on line. And this time your cursor again changes to, and this time change it. Okay, I have done it a little wrong over here. So this is my Keepout Layer. And I'm just going to keep it here. This is my Keepout Layer like this. So Keepout Layer is the margin of your PCB, which you are actually going to tell your manufacturer that your PCB is going to be of this much margin. So now what you have added over here, you have added the margins over there. And since you have done it with the mouse, please every time, please correct these ones. They should be in exact rectangular or square shape. The angles over there, this one is, it should be 90 degrees. This is the margin. This is the margin of the PCB. This one. ये आपको manufacturer ने cut करके देनी है. From the big PCB sheet, whenever they are going to make the PCB, this margin will be cut by them. So you are actually telling it. अब अक्सर बच्चे ये करते हैं कि whenever they are designing a PCB, if you keep this margin, supposedly आप इस margin को, you select this margin and you keep it like this, किसी जगह होगी. The problem would be the manufacturer is going to take the price of the sheet of that PCB per square inch. So it's very important your size of your PCB is as small as possible, and the margins should be at 90 degrees like this over here and like this one. ये कर सकते हैं, ये मैनुअली है, सॉफ्टवेयर से हो रहा है. ठीक है, ये आपने मैनुअली, मैंने क्योंकि क्लिक गलत किया, I clicked it in the wrong direction, that's why it was happening. So this is your margin. Now still there is a margin available over there. If you can see, as I can select it, you can change the margin a little bit more like this, and similarly I have a margin over here as well like this one. Now I told you in the rules over here that the Keepout Layer has to be a track of 0.6 mm. How to do that? Since when I go in zoom, click on this, double click on this one, the dialog box opens and the width is just 0.254. I want to make it 0.6. Now how to do that? Very easily, again go on PCB filter, go on the builder and select object kind is, where is my line actually, where is my L line, I can't actually, in fact let me not do it, exist on layer, where is my Keepout Layer, okay, Keepout Layer, apply all, and now you can see all the Keepout Layer of margin is selected. Click on your properties, here change it to 0.6 mm. Now this margin is still relative. Now this is a must. Please follow these rules which I have given. The pad size 2 mm by 2 mm, wire size 2 mm by 2 mm, Keepout Layer 2 mm, track size 0.8 mm, then coming on to the 3, 4, 5 just now. Now when you have done it, you have to add your name, your group number and your experiment number. How you are going to do it? Go on place, click on string. You have to add a string over there. Your mouse has now that string. You can use your space bar whichever direction you want to. Place it over there, and as soon as you will place it, double click on this one. A dialog box open. Here you can write anything. Again, since you have designed your PCB, just the first name. ये नहीं है कि पूरा नाम लिखने बैठ जाओ. The space is going to be used for that purpose. We only just want to have a identification. Arslan written over there. Mirror it. Now why I am mirroring it? This is very important. When you are designing this PCB, let me just go back over here. When you are designing this PCB and it is in front of you, let me just see over there. This is in front of you. I will just close this one. You are seeing the PCB in your hand. You are seeing the top side. The name is going to be printed on the bottom side. So that's why it has to be mirrored. The manufacturer will know that since this is a bottom layer PCB, they will make it upside down.
So they will automatically do it because you are seeing the name from the top. That's why it's mirrored. So this Arsalan, double click it again over there and click this box, this will be mirrored. Now, this name should not be extraordinarily large, should not be extraordinarily very small. What are the dimensions which I have asked you? The dimensions for this string are 2.5 mm height and 0.5 mm stroke width. And that are over here, text height, make it 2.5 mm over here, and stroke width over here 0.5 mm. Okay, sorry, this is 0.5 mm. So you can see now this is on this file. It has to be mirrored just like this one. Again, group number, whatever you have, B1, your PCBs are going to be individual, remember, but still this group number is to be done by you. Your PCBs are going to be individual, at least for experiment number 6, 7 and 8. But you are going to design it individually and make it also. After experiment number 8, then we will move on towards the group PCBs over there. This is because last year many of the students were not soldering. Group member एक काम करता था, दूसरा काम नहीं करता था. So just to make them work, every member has to design a PCB and submit it. And क्या हो सकता है? नहीं. That is a cheating case straight away. So this is very important. ठीक है जी. So please. So this your name. Your group name B1, B2 or whatever you are, section D over here, and then experiment number 6. These three at any adequate space. ऐसा नहीं है. Remember one thing कि आप ये कहो कि अच्छा यार हमें PCB थोड़ा सा यहाँ से बड़ी कर दूँ और इसको ड्रैग करके मैं को यार क्योंकि मेरा नाम है जरा शान से आना चाहिए यहाँ पे. So इसको यहाँ पे अलग से. So you are going to pay the cost of that PCB by the size increase over there. तो जी वो इस तरह से आप कर दें. Please adjust your name, your experiment number in the vacant spaces of your track. This. Okay, now if you see the dimensions, now how you are going to put the dimensions? The last thing is you have to put the dimensions. Listen this carefully. Go on place, click on dimensions, go on standard. Where is my standard actually? Okay, this is standard over there. As soon as you will click your standard, your mouse cursor changes to again a star. Zoom it by your scroll key and that one. Click it, drag it and keep it straight. This is your first dimension. Now one thing very important. Since I am just making it a little estimation, ऐसा भी नहीं करना. Some students do it like this. Don't do it slanting. Keep it as straight as possible so that I know whenever you have submitted your design and I'm opening your file, I know okay this is 57.531 and the length other dimension, again going on dimension, standard, again click here just by estimate and keep it as straight as possible. And now this is approximately 90.678 or 91 mm. So this is 91 mm by 57.531 mm. But yes, I have wasted some space over there for my name. So I can reduce it down more over there. So I can take this name B1. Again, all of these are to be mirrored. So this is very, very important over there. And you can again then reduce the size. You can see how much space I was wasting. So now from 91 it has reduced down to 84. So smaller the PCB. Now for experiment number 1, maybe this experiment number 6 actually, which is the PCB of experiment number 1, I'm not going to be very strict on the size dimension. But remember, larger the size, larger is going to be the cost of your PCB. But as this experiment goes on to experiment number 7, experiment number 8 and so on, size will be a very constrained factor in those experiments over there. Here you can design a PCB somewhere in between 57 and 85, that is still okay, nothing fancy. But if you can see over there, there is a lot of vacant space here, a lot of vacant space here, a lot of vacant space here. These should not be there. A well-designed PCB is that in which vacant spaces are not there. Now the last thing, very last, please no talking. Over here, if you can see, the track width is 0.8 mm. Now this is a very small experiment in which experiment number 1, the circuit diagram is not having that much current. But as this experiment is going to go towards experiment number 2 circuit diagram, 3 or an RGB, the current is going to be huge. In that case, either you have to increase the track width or you are going to increase the fill area. Now what is the fill area? If I go back over there, if you see very closely over there, this pad and this pad, they are connected by a very thin line and they are taking the total current of the IC or the PCB. So instead of just a very thin track, what I can do, go on fill area, place, click on fill, and this again changes my cursor, and now this time I am going to make a fill area like this, and I can just drag it a little bit and make it like this. Now what has happened, the fill area is having more copper. It can sustain that current. Similarly, not just the VCC, now I can do it for the ground as well, because current agar VCC se ja raha hai, ground se wapas bhi aana hai usme. It has to come back. So I can do it for the ground as well, and you can make this like this, one PCB, one fill area like this, and as soon as you click it, it takes that net automatically. And now here you can take it like this over here. So this is a fill area placed, and here I can make it a little thick over here like this. Now you can see what I have done. When I place the fill area, it is very close to VCC. So it has taken that green color. So I have to again bring it back to some adequate size. Now I will advise and I will encourage it that even for experiment number 1, use fill areas at least for VCC, ground and input. Wherever there is a VCC, ground and input, use fill areas so that your PCB can sustain that current. Now the reason also I am asking you to use fill area, because if there is just a one simple track, when you are going to solder it, and I guess you have experienced it, that on your wear board, if you keep your soldering iron for a very long time, the track erodes off. Yeah. Similar thing can happen on a PCB. Okay. So to avoid that process, please make it fill area so that you can have the current also heavy. Now these tracks which are connected from one resistor to 7 segment, there is no need of any fill area. They are very simple. They are not having that much current. But yes, when you are going to move towards a yellow dot matrix or an RGB dot matrix, yes, certainly then we will ask you to increase the track size. But overall, as far as this is concerned, this PCB is going to be designed in such way. Your design dimensions are something from 57 to 85, or you can call it 90 mm just for sake over here. But remember, tracks should not be close like this one. You have to make them a little far apart. But when I mean by far apart, this distance between A and F and A and B is adequate. This can be done very easily. The manufacturing process is also not going to hinder in this one. But you can see when this track is going, it's bending a lot. And when there is a bend, it's also always going to have some parasitic inductance or capacitance, and the manufacturing process is going to eat away the etching solution, is going to eat away the track. That's a big problem. So please design your PCBs over here. This is your experiment number 1. And I guess you have the experiment number 1 circuit diagram with you. You have your experiment number 2 circuit diagram with you. You have to submit both of these PCB designs, which means you have to submit me the PCB doc file. This is very important. This is experiment number 6 over there. This will be a PCB doc file. I will share the link with your CR where you have to submit me the PCB doc file, and this has to be done before your Eid holiday. This is very important. Before your Eid holidays, you have to submit me this PCB doc file, and it has to be, remember, next thing please, it has to get approved before your final exam start. And when I call it approved, this means that I will return that file to you with some reviews. Okay? That review will be given to you. Supposingly you have designed a PCB, that in that PCB you have not mirrored your Arsalan name or whatever your name you have. So I will ask you to mirror it. All the dimensions are a little bad, or your tracks are not very far apart. Then I will give you, and then you will resubmit it me on that preferred link with that attribute, whatever we tell you, and then you will, and when it is get approved, when you will come back after your midterm, you will have ordered that PCB to the manufacturer, and you will bring that physically made PCB over here in the lab, and hopefully on camera again I will solder 1 or 2 PCBs in front of you, and then you can solder it and again run it. Okay? So before Eid holidays, your experiment number 1 and experiment number 2 circuit diagram, which are now experiment number 6 and 7. If I can show it, this is experiment number 6 and 7, the PCB design of experiment number 1 and 2 circuit diagrams. So this is your task over here. Before your midterm, you have to get it approved before your midterm. Submission the first has to be before your Eid holidays, that is supposing you can call it Monday. So I will give a deadline of Sunday. So your first submission will come to me on Sunday. This is very important for all sections. Every section has to submit it on before Sunday. I will give a review on this one most probably by Monday or Tuesday, and then I will give a deadline of maybe 24 or 36 hours, and you will have to resubmit me again. And you have to get it approved. If it is not approved, you cannot proceed with the PCB manufacturing, or you cannot order it. This is very important. So this is all for today. This is your Altium software, and I hope you have got the idea what we are actually trying to do. This is your experiment number 1 circuit diagram and experiment number 2 circuit diagram which you have to do. Any questions with this one?